All attendees are in listen-only mode.
Attention now, please. We're ready to begin for today. I want to welcome everyone to today's sustainability seminar. As most of you know, my name is Nancy Holm, Assistant Director here and also the seminar organizer. For the seminar today, we'd like to ask you here in our audience to hold your questions until the end, and then we will answer those, and we'll also answer the ones from the listeners online at that time. They can type those in, and then we'll read those to the speaker and answer those for you. So before we get started today, I wanted to just mention we have two other seminars coming up in April. One we advertised as a sustainability seminar, and one is just a new research seminar that we're adding now for next Thursday. So next Thursday noon, April 18th, we'll have a seminar presented by Professor Karen Nguyen, who is Associate Professor of the Department of Material Science and Engineering up at the University of Toronto. She will be visiting us here to talk to June Wab about his research and was kindly agreed to give a seminar. So for those interested in her work, she'll be talking about polymer electrolytes and their application in ultra-high rate solid electrochemical capacitors. And then the following Thursday, April 25th, will be our last sustainability seminar. We'll have Dr. John Rogers from the U of I here, the Department of Material Science and Engineering, coming to talk about his research in water-soluble electronics. So I hope you can plan to attend those two seminars, and for those listening, if you want to register for those, we'll be sending out more information about registration in the abstract. I have printed the abstract for next week's seminar. If anyone before you leave, we also have today's abstract, and then on the 25th available on the side table here. And again, those will be accessible on our website also. So today, then, I would like to say that we're very pleased to have with us Dr. Luis Rodriguez, who's Associate Professor in the Department of Agriculture and Biological Engineering here at the University of Urbana. Dr. Rodriguez's research focus is on multi-scale modeling, systems engineering, and analysis of biological systems, on reliability and sustainability, and on decision support and market support. He received his PhD in industrial and systems engineering and bioresource engineering from Rutgers University. He also received his master's and BS degree there in bioresource engineering from Rutgers. He's been a professor here at the University of Illinois since 2005. Prior to that, he was a research scientist from 2004 to 2005 at the university's Space Research Association, NASA Johnson Space Center. He did a postdoc research associate position from 2003 to 2004 with the National Research Council. And then he was a senior principal systems analyst in 2000 at the Orbital Space Sciences Corporation for NASA Ames Research Center. So with that, I'd like to please ask you to join me in welcoming Dr. Rodriguez.
All right. Thanks so much, Nancy. That was a great intro. Too much, really. And thanks for the invite. I do appreciate it. Whoa, we're already on the second slide. There we go. So I'm in agriculture and biological engineering. I also have some affiliation with the Information Trust Institute. Information is very important for my work. We want good quality information for our modeling and analysis work. A big portion of what I've been doing lately, especially since coming to the University of Illinois, it has been in the area of biomass-to-bioenergy. So I'll be talking about that for the bulk of today. We do use those same modeling analysis techniques. I guess you might have heard it in the intro. NASA and life support systems was a big part of my work prior to coming here. And we're moving to other parts of the Earth as well, particularly studying carbon balances and nitrate and water systems as well. And I'll give you a very brief overview of those towards the end. Primarily today we're going to talk about some of the methods behind our work, and I'll show you 3 different models as examples of how we've studied biomass to bioenergy provisioning, and give you some ideas to how we are planning to expand to some other areas. Now, I think you know this, so some of these things I can go through quickly, I'm sure, but primarily we are anticipating that the next most likely source of large amounts of fuel and energy might come from biomass, cellulosic materials being converted into things like a bioethanol or some other solid or gaseous fuels. That suggestion comes generally from our Renewable Fuels Mandate and some of the billion-ton studies that were published by the DOE. Really, going forward, corn and corn to ethanol is probably maxed out. We need to be going somewhere else. Cellulose then becomes probably the most available molecule on Earth, so that might be the next place to go in order to harvest some energy. That red stripe on top is other biofuels. You can see that even 10 or more years from now, the best predictions are suggesting that's really going to be a small portion of our energy source. Not that that's not going to be an important place to be studying, but probably right now we're talking about something that relates to biomass and so on. To get that to happen, however, to get to a billion tons, new supply chains are going to have to emerge. They just don't exist right now. The idea would be to get to several hundred conversion facilities across the U.S., and at this point we have maybe 1 pilot scale, maybe 2. There's not that many out there. Maybe one of them is even in this building, you might say. So how are we going to do that? This is a very typical supply chain diagram. This is one that, in fact, I use for my teaching on a regular basis. From the perspective of making things sustainable, it's very important that we, as engineers, as we design our systems, are considering that resources are consumed at every step, and those resources have impact. We have to get those resources. Residues are produced at every step. Transportation is used at every step. And this actually really becomes the underlying theme to a big portion of a lot of the work I'll be discussing today. Each of these steps are critical. They impact one another, and resources and residues are created at each step. So let's take a look specific to biomass to bioenergy, and maybe let me start giving you a flavor of what we're going to be talking about. Primary production, where we start to get our resources from. Primarily this is going to be, at least in my studies, crops dedicated to production of biomass. So land would be consumed in order to make that biomass. No grain is involved. Non-food biomass crops is what I'm primarily looking at right now. Some of my interests in the future do consider some other biomass sources. I'd be very interested in studying things like municipal solid waste and biomass within this into a supply chain like the one we're talking about now. But if we're going to talk about crops, for example, what are those harvest technologies? Yes, we do handle biomass on large scales already in crop production systems. But when we're talking about hay, it's a little bit different than what we're talking about biomass dedicated for production here at a scale that we're talking about. So harvest technologies do need to be considered, probably improved, operated better. Packing technologies, this is how we're going to first start densifying this biomass. Relative to coal, biomass is a very low density product, and it becomes very hard to move this material through a supply chain efficiently. Scheduling becomes very important. I think I'll start to show you some examples of that in a little while. Scheduling is going to be a really important thing. At processing and manufacture, especially in this part of the temperate zone, we are really looking at a situation where harvest is going to occur once or very few times throughout the year. Meanwhile, a conversion facility, be it bioethanol or something else, is going to want to convert biomass steadily throughout the year. Storage has to occur. What is the right form of storage? Till now, most of the people we've been working with are looking at biomass as a very stable product. I guess there are those out there that maybe not so convinced that it's how stable it might be. So the quality of storage becomes interesting. We studied open and covered storage, keeping weather away from the biomass pretty extensively. People are talking about climate-controlled storage, although we haven't studied it yet. But processing starts to occur right away. densification, all the way to maybe things like pellets, but also chemical or physical pre-treatment in order to make that biomass material more amenable to conversion is also things that we're looking at. Scheduling again. Now, depending on what you want to do with the biomass is really going to have a major impact on, as to how you might build your supply chain. That is, the end conversion that you're targeting, the end use that you're targeting really does change the way you might be looking at handling your biomass upstream. So we are looking at a few of those too. Primarily bioethanol I'll talk about today. See, trucking in the way, transport in the way of trucking, rail, barges, what have you, are all being considered as well. I'll be talking about mostly trucking today, but we're just starting to publish right now on rail and presumably barges in the relative near future too. Now, our work has generally been in models. That is, we are trying to study these systems on computers, and in order to facilitate a lower cost analysis of these. So we are trying to build some models that are representative of a physical space and provide advice back to folks who might implement these systems or give people advice on how to implement these systems, like over here at the ISTC. So it's an iterative process, though. That is, we're in a very fortunate situation right now, and I'll talk about that in a minute, but we're working very close to people who are developing and implementing technology as we develop these models. That feedback loop is indispensable in us being able to do good work, and so I think I'll be able to emphasize that a little bit as well. Now, John, I see, he took this class a little while, but he's seen this particular slide a while. I have several steps of modeling analysis that we generally repeat and repeat and repeat over and over again in that cyclic feedback process that I described before. This is, again, a teaching slide. What I want to emphasize right now is that if you also take a minute to go look in the published research, almost out of all of those steps, and you can see them in various forms in various systems engineering handbooks, almost everything is published in the area of I'm going to make a better model or I'm going to analyze your system in a slightly different flow. I guess to give you a little bit more information about myself, some of the themes of our research are really in order to enable that whole process to occur seamlessly. Bring information in, as I mentioned, from some of our collaborative technology developers so that we can analyze it as rapidly as possible. Hopefully provide good advice back to those folks who might be developing technology. That's a rather long-winded introduction. Most of the work I'm going to talk about today has been funded generously by the Energy Biosciences Institute, the BP Center located at UC Berkeley and here at University of Illinois. We're a program, this is a slide dated March 2013. I'm a small cog of this particular system, but there are several of us PIs, 6 total on this particular slide. Several postdocs and grad students working with us as well. So I'm going to be talking about the work of several people. And we divide ourselves into 5 different sections, areas of specialization: harvest, transport, storage, pre-harvest, as well as systems informatics analysis. So I conveniently put myself right in the center of all this, as you might notice already. But the idea is that we are trying to leverage those developers in each of these areas and hopefully feedback. I will be talking about work of all of these people in some way, shape, or form. How are we organizing ourselves right now? I mentioned that I was going to talk about 3 models in particular. Those models are focused on different parts of how we make decisions in order to bring these systems to life. Strategic level decisions, tactical level decisions, and operational level decisions. So I'll be talking about 3 different models: bioscope, biofeed, and biotrans. Biotrans is our most recent addition, so I'll only have some very preliminary stuff in that particular area. At the scoping level, we're really talking about where are our facilities going to be located, how big are they, and how much, where should they be sourcing and sending the materials to. At the tactical level, biofeed, where I'll start my discussion in a moment, we're going to be talking primarily on selecting equipment for use on specific locations. Imagining you have already selected the best place to put your business. What is the right equipment to operate with, and how do we operate it? And then environmental biotrends on a day-to-day basis, if you're going to operate it and you need to move 5 tons, 500 tons, 5,000 tons of biomass today, how are you going to get it done? These are the types of questions we're seeking to answer. I'll start with that biofeed model, the one that we're targeting at tactical level decision making. It's our most mature modeling effort, but also I think it provides the best view of how much depth we are really getting to. So if we're growing biomass, a dedicated biomass shop, and we need to get it to a biorefinery, what are all the steps that need to occur? They'll be in the farm in part and in a transportation system and in a storage and pre-treatment system in some way, shape, or form. When we first started this work, BP, EBI hired us. We went out and the first thing we said, well, let's go get the most biomass we can possibly get. That would suggest, perhaps foolhardily, although I think this is another topic that's being debated, we'll harvest at peak biomass in the field. Grass is very green and very pretty out there, very tall. You get the most biomass out there possible. You've got to store it. That might look like an silage process after you store it. There's a lot of biomass out there. The agronomists tell us don't do that. So this is where we start to see where our system has a few constraints that we can't just do anything out there. The agronomists tell us not to do that because many of these biomass crops will take nutrients from the soil, put them into the green biomass, and then return it to the soil later, greatly reducing or perhaps even eliminating any fertilization requirement on the next season. That's a pretty nice feature. After that, they pushed us pretty hard away from this into some other areas involving dry biomass, biomass that's well past the senescent state. If you do that, you'll also focus your harvesting window considerably. Several things end up needing to occur. You want to get that biomass into a smaller format as quickly as possible. This involves packing. The most standard technology here is bales. You've heard of those, but we can pelletize, chop, grind, make a fine powder out of this material. There are costs, of course, for making these things to occur. Some of the scientists that we work with that are looking at some of the conversion technologies ball mill their biomass to 80 microns particle size. That's a lot of energy to make an 80 micron particle out of a piece of grass, a large piece of grass that's stiff like that. You probably wouldn't do that. You were probably trying to get to somewhere in between. The question really starts to become, and that's why we have several options, is how small is the right size, and what are the cost or environmental impact implications that you might be expecting. Now, all that material, it needs to be handled. There's a non-trivial amount of biomass handling and in-field transport that occurs even within the farm. That is, if you're a farmer and you know you're going to store some biomass on your field, you're probably going to allocate the little corner of your field that you might think is the least productive piece, and you're going to store it all there. That biomass doesn't magically get there. You're going to have to pack it up and make it go there. You might bale it, throw it on the back of the truck. You have a loading and an unloading operation in order to make that occur. Further, you might even invest, if you're a farmer, on at least a pole barn or a four-pole roof structure in order to keep the material out of the weather, or you may tarp it in order to keep it out of the weather. All those things are often going to have impacts on how the biomass stores. Our model work right now, it does consider things like the moisture content of the material, because that will be associated as to how fast it degrades in the field, and that is a function of the configuration of how it's stored. Now, that being said, all of those technology that are available for on-farm storage could also be done in a large centralized location. So we have that option there for storage as well, but that starts to require a larger scale of transport, which moves the material tens, maybe even hundreds of miles off of the farm to a centralized location. At either the farm or the centralized location, you might be doing that size reduction step. You might start with bales and then move to pellets later, if that ended up being beneficial to your system. So. Now, for the most part, we are looking to determine the optimal configuration. And we have to have a definition as to what is optimal. We're looking for what is best, and there's all sorts of ways to start thinking about that. Part of that systems process that I alluded to before requires us to think about what ways are best. I think your center already does a lot of this on a regular basis, but the bottom line is we need to have somewhere to measure and compare systems and do it from an objective perspective. Our current model objective is primarily to maximize the profit of the supply chain. Really, this is another way of saying minimize the cost of the supply chain. They're almost the same, not quite, but almost the same in both cases. You can look at sustainability in a number of different ways. We have colleagues in other parts of the EBI that are looking at various parts of life cycle costs. And for them, life cycle cost is not just greenhouse gas balance or net energy consumption, but they're also looking at things like particulate generation. It's not a particulate generation right now. They are thinking about a number of other ways. If we come back to that, ideally, of course, we'd also like to get to some social impacts to the farmers. Yes, a question. Yes, yes, absolutely. I was going to let you know in a little while, but I'll go ahead and tell you now. We are using a mixed integer linear program in order to solve this particular system with constraints that I'll be describing. In this particular case, yes, we've built the system with linear models, and so it's mathematically provable that the optimum we find is the true optimum of the system if our constraints are really true and if we really had control of every part of the system. And please continue to jump in with questions. My dad chastises me. I talk fast. That's so, okay. And I'll have to remember to repeat the question. That particular question was just about whether this was an optimization problem. So, hold me to that, Lindsay. Maximizing profit right now is really how much is the profit of the material being sold by the biorefinery. This is very biorefinery-centric right now, I'll admit. But it's material sold by the biorefinery, and all the upstream costs are being subtracted from that potential profit. Harvesting, packing, storage, transport, costs, biomass handling costs are all being considered. So, as I mentioned, we're working with a linear optimization program. It is possible to get to a true optimum of our system if we define it based on constraints. For the most part, our constraints are really physical and chemical limitations as to what it takes to manipulate material off of the farm through a grinder, or a chopper, or a baler, into trucks, rail, what have you, and delivered to a system. All of these things are throughput through machinery that we might have available. We've spent some time trying to assemble that type of data. We have a good idea as to what type of machines could be used in a system like that. These are commercial pieces of hardware for the most part, although we do also spend some time thinking about some of the research hardware we work with too. I'll give you a feel for it now. I'm going to run through a number of constraints. This is the real dull part of the presentation too. We can come back to it too. So don't be shy about asking questions about it. So if we start from here, capacity constraint. Every machine has a throughput capacity. We can store a certain volume. We physically do allocate the size of a storage facility, the height that you're allowed to store things to. These are all decisions that we deal with as input to our system. If you're using a tractor trailer, you can move about 30 tons of material. It turns out you can also, I don't know the volume off the top of my head, you can also transport a maximum volume on the back of those tractor trailers. Both of those are constraints. Quality constraints. I mentioned moisture a little while ago. We recognize that we are losing biomass as time goes by in our system as a function of the moisture content. Depending on what part of the year we are assuming we harvest the biomass, we assume the biomass has a different inherent moisture content, and that changes its degradation rate. Our system is not working with an infinite set of machinery. Farms have a selected number of harvest, transport, storage machinery that they can allocate towards the system, and all of those things are limited by their availability at any given time in our analysis. And cost. Cost becomes our big key, of course. We are considering capital and operating costs for all these things. Generally, our costs are amortized over a 20-year period, and we'll start to see some of those impacts as well. Labor is considered in our model. So similarly, those were some of the constraints. Not quite a complete set, but it's pretty close. We also are making decisions on a number of things within our particular system. How many machines? What farms get which machines? When will harvest occur? What time of year? Where will you move that material once it's been harvested? Can you harvest a portion of a farm, store it on the farm for a little while, and later in a centralized location? We are considering storage decisions, the quality of the storage, the quantity of the storage, the location of the storage we are handling as well. Number of trucks, this becomes pretty interesting. The number of trucks required to manage the system. We have a transportation fleet, effectively, that we're sizing based on the decisions made by this tool. The refinery itself, how big can it be? We can use the system to optimize, minimizing cost for a refinery in a particular area, or we could turn that around and make it a constraint. I want to process 5,000 tons of biomass per day. What does that cost? We can ask the question both ways. So all of these we generally look from as decision variables for the most part, but we can turn them around and make them into constraints. So we started with switchgrass in our particular area. Switchgrass simulation horizon starts in September, the first day of switchgrass harvest. It'll end on August 31st. By August 31st, we have processed all the biomass. We have sent it all to the biorefinery. They are converting it. There is a horizon. We must harvest all your switchgrass in about 120 days, so by the end of the year. And then we use data regarding a specific region. We're working in a region in southern Illinois. I'll show you some images in a little while. That allows us to understand how big those farms are in that particular area, where they are, what their yield rates will be, and where physically they are located. So we are actually specifying a certain part on our map. Now, this is an example of some of the results we get out. It costs a little less than $50 a ton to process the switchgrass biomass, moving it through the supply chain that we suggested. That area in southern Illinois, it's 13 counties. The postdoc, we call them 17,400 square kilometers in that area, of which 30% of the farmland in that area is allocated to it. That's the total area of those counties, 30% of just the farmland is allocated to switchgrass. The cost breakdown starts to look something like this, where we're spending quite a bit of our money in the transportation phases, but not nearly as, with a significant chunk also occurring in harvest. That is, it's big material that you're starting to do. On the right side for you, you'll also see some data describing if you could improve this system, which part should you improve first? The first thing ended up being, can we reduce the amount of truck idling time in the particular system? In our case, we selected that we're going to have precisely one storage location, precisely one biorefinery, and deliveries start to occur September 1st. What ends up happening is queues start to form at these various locations because of the amount of material. You're going to get, the way I show it, almost a one-to-one bonus for if you start to reduce idling time, you can also start to reduce your cost, your system cost. Packing density, we spent a lot of time thinking about. In fact, our transport team in our EBI program started to work on how do we pack this biomass better, size reduction technology. There's a pretty good bonus there, and we actually came back to study packing in particular. Yes? So it's a good question. The question is why did we select this particular location in southern Illinois, these 13 counties? We did spend some time looking at the available data that we have regarding how much yield you would have in switchgrass, how much was the opportunity cost of those lands if they were assuming to be growing corn and soybeans as a major business already. That pushed us south. Opportunity costs for corn and soy are much lower in the state of Illinois relative to the rest of the state, and if so, they still had some pretty decent yield. That became a pretty nice area to start, assuming we would produce there. But that is input. That is definitely input to our model. That strategic level model I alluded to earlier, we're going to go to that in a little while, and that's where we start to say, well, where is really the best place? You'll see a little bit more of that in a little while, graphically on a map. At this point, you can also get a feel. 81 trucks are required, but 76% of the fleet is utilized on average. That is, a quarter of the fleet is idle. During the early parts of harvest, you need every single truck every day for a little while. As most of the material gets out of the field, getting close to December 31st in these assumptions, you've moved most of the material almost all the way to the biorefinery. At least a quarter of the fleet is idle. If I'm a trucking company, that's not the way I run my trucking company. No. Maybe we ought to be renting trucks for a system like this, or maybe some other ownership pattern should be considered here. That's something we are looking into. Yes, I heard a question. So the way when we're looking at it from the perspective of we're going to minimize the whole supply chain cost, you are really saying that one owner owns not just the biorefinery, but is controlling all of the land, can make decisions to allocate all the machinery, and specify harvest and planting dates. So there's one owner from this particular perspective right now. We do have some other work. Unfortunately, I'm not going to talk about it too much today, where we start to discretize the system into independent agents. You might have a very different story if you were renting your trucks on short terms or something, or contracting out. Very different story, potentially. All right, so let me repeat the question, and correct me if I'm wrong, sure. So the initial question was really who is bearing the costs of the allocation in the pie chart that I'm displaying right now. And that's why I said really there's one owner. And the response is maybe we ought to be renting or contracting our shipping and our transport. And maybe that is what we're actually doing. It depends. It depends. It turns out, and maybe I should have shown some of the other analysis I just alluded to, if a large consumer like a biorefinery is willing to go get their feedstock, you can actually greatly increase the capture of farmers who are willing to get into your business. If you instead transfer that transportation cost to the farmer and allow them to try to negotiate a cost where the sale price includes not just the biomass but the transport that the farmer would incur, you greatly lose farmers to come in and play that particular game. Now, that being said, ADM, you mentioned ADM is not necessarily the best example. It turns out that they do a lot of their own trucking and shipping. So we can come back. There's a lot more I'd like to show you too. I want to start talking about the bioscope model and see about how we can start selecting those best locations. And what we started to learn from that previous model is that really you do need a centralized location of transformation, processing, and material. Why? Because a biorefinery probably is going to be very interested in having a uniform feedstock arrive at their doorstep. That previous analysis I showed you at $50 a ton is suggesting that farmers who it benefits them to send a bale, they send a whole bale, but if you can afford to chop it down, you send it chopped, and you might get a potpourri of different types of material. This particular analysis, on this slide suggests that we're going to have a three-stage supply chain where the central supply chain works on uniform feedstock provision. Okay? So the center layer there, those are CSP, centralized storage and preprocessing facilities. And what we're going to do now is select which is the right farm, which is the right location for the CSP, and which is the right location for the biorefinery. And as I mentioned before, we have a pretty good idea based on some models and experimental work on the left, where is the biomass available if you were to grow it in those regions. And this is considering a 2% conversion of biomass, very low conversion. And on the right-hand side, we also, using that biofeed model, can predict how much it costs to deliver that biomass. And if you overlay these two, you can start to see, and maybe it's a little difficult in this view, but you can start to see that Southern Illinois seems to be pretty beneficial. And that's in fact what this particular optimization also showed. It's again a mixed integer linear program, minimizing cost overall for the system. And it turns out that Yogendra's counties, they are in this range here, and I'll show you which ones they are in the next, the next slide. The cost breakdown does change a little bit when you start to select the best location. You see those triangles, many, many, many more CSPs, many, many more centralized storage. For one centralized biorefinery to deal with 2 million megagrams in the course of a year. This is a much bigger system. Land conversion very low. Okay? Now, half the cost, nearly half the cost, still is in the hands of the biorefinery. The other half is delivering the material. So that's not trivial. If we can do a better job delivering, I'm sure we can have some impact. So, for example, we began to say, well, what if you start playing with that cropland conversion rate? What if you could really convince people to get into this business? Yes, definitely your region does start to get a lot more focus. It turns out that Yogendra is very accurate in his initial assessment. Letter H is a 20% land conversion rate, and the location of the biorefinery is just about one county off from his original guesstimate at that particular time. We've also, now this is of course, different land conversion rates still want 2 million megagrams in a year. But where's the next biorefinery going to show? What impact is that going to have? So if you had that first $2 million megagrams in 2012, and somebody else wanted to come into business in 2013, and somebody else started coming into business in 2014, 15, we pre-specified some new demand and supply growth rates. What does that start to look at? At least monetarily, the cost does start to come down. It's less than $200 dollars per megagram total delivered ethanol cost. It's on the vertical of this particular chart. Not too bad. The major gains are in economies of scale. Economies of scale, particularly the biorefinery. It's still very expensive to convert biomass to cellulosic ethanol. You also see some improvements in the transport. Why? Mainly because that region is so much more concentrated over time. We play with this also by considering some contract lengths. A lot of our work is also in miscanthus, a perennial biomass-to-bioenergy crop with probably a working field life of 15 to 20 years in the field. People don't come into that lightly to get into a business for 15 to 20 years. So, for sure, question? So, I have that in a upcoming, no, I think I have it here. So the question was, what is it per dollar per gallon as opposed to dollar per ton? $220 per gallon per megagram is roughly equal to $2.8 per gallon. Now, I want to mention at this point, we've spent some time also considering, this brings it to the biorefinery, what if you're going to blend it and sell it to people at the pump? That really does have a major impact. Although the net cost of that step is really less than, if I would put it under this pie, this is very new work right now. If I would put it under this pie chart, it's not 10%, it's probably about 7% of the total cost to blend and deliver to a pump, the ones that we use. It does push the places where you do want to source your biomass significantly far away from southern Illinois, rather closer to the major cities, closer to where your consumption points are. Actually, no, I wouldn't agree with that. So the question was whether this is close to the DOE target cost or not. At that point, we're getting to about $1.8 per liter, and I think they're looking at closer to 3 as a target cost, 2. So we're really starting to get into the ballgame, I think, at this point. A question in the back. For the biomass, I'm referring to a completely converted ethanol price. So that includes the delivery. So if I come back to the delivery of the biomass in this particular system, we're getting close to 35, not 235, but we're seeing economies of scales and conversion that maybe that we're not being seen by the DOE. Go ahead. Right. So if we could incentivize, the question starts to come back to incentivization of getting farmers into the business and whatnot. Road taxes are particularly beneficial. Establishment costs are particularly beneficial, we've seen. Of course, establishment incentives are probably going away if they even exist. So the last portion, am I all right on time? So the last portion, I wanted to get you down to the operational decision making, give you a feel for what we're seeing right now, although this portion is not complete as of yet. We have started to build some web interfaces for dissemination of these tools in the form of decision support. They have a database backend, several servlets in order to receive requests from users and send out some information. Now, that is, you or I could be on the front end as a user. Some of the information might start to look like this. What is being displayed right now, there's sort of a spider web network of pinkish and reddish lines. On the outer reaches of this spider web network, those are farms delivering biomass to locations. If you look towards the center, you'll see some a green pin and a magenta pin. The green pin is a storage location, and the magenta pin is the biorefinery in this particular system. This is back to Yogendra's counties. Those are his 13 counties being displayed right now. And in this particular case, he had one storage and one biorefinery, as I mentioned earlier. On the first 15 days of his simulation, he recruits 113 trucks, if I remember. Yeah, 113 trucks to start the harvest operation and start delivering biomass. And our optimization scheme tells us precisely which farms. There's about 105 farms on this image right now, of which I think about 80% are being active on the first day to deliver biomass. Some of them will start their harvest a little bit later in the season. And they're delivering it either directly to the biorefinery or to the storage location. The intensity of pink and red is how many trucks are going to be on those roads. What is the added load to those roads in the way of biomass being transported down Illinois highways to the biorefineries? The deepest shades of pink and red are referring to about 20 to 30 trucks to a biorefinery that's handling about 2,000 tons a day of biomass. The pie charts below have all of these periods. I can produce the little spider web map for any 15-day period during the harvest season and some 60-day periods after the harvest season. There's a lot more activity going on during the harvest season as opposed to the non-harvest season. The pink shade in those pie charts, no, sorry, I made a mistake. The blue shade in those pie charts are the idle trucks I was referring to before. So in the first 2 weeks, every truck is being utilized, but it's much less over the rest of the season. Some of those deliveries in green or in pink are either directly to the biorefinery or to storage locations. Now, this particular system helps us understand where our system is going to go, and you start to collect from all parts of the field, all parts of your 17,400 square kilometers in those 13 counties. We're going to start bringing things in. Our funders in the Energy Biosciences Institute, they found this particularly curious. They really thought that the logical way to go would be, I'm just going to go get biomass from the first kilometer radius, and then next week I'll do the second kilometer radius. And that's not necessarily the cheapest cost solution. This should get us closer to the cheapest cost solution. Now, if it was your job to deliver those 2,000 tons and you had to tell the trucks to dispatch first thing in the morning, we're trying to create some interfaces which blue and red trucks will dance around on a map, going to pick up biomass, turning around to deliver it to a location. What we've learned right away in this particular analysis is that our first logical but foolhardy assumption is that at 8 a.m. you would dispatch all your trucks, 113 of them. And it turns out that they all get to their destination from the depot at about the same time. They turn around and come back, and guess what? They arrive at the storage location at the biorefinery at about the same time. Large queues start to emerge. It turns out if you dispatched all your trucks all together at 8 a.m., you will not finish your deliveries for the day. It would be impossible to finish your deliveries for the day. So it turns out that you need a little bit more of what is UPS's slogan these days. You need a little bit more of an intelligent approach in order to handle all that dispatch and handling. So we started building some optimization tools there as well. We want we know the cost. We've already predicted a reasonable cost measure. Now we want to see where's the right optimization to minimize some of that idling time. Lo and behold, some of our preliminary results right now, I'm not going to be able to show it. We can get rid of all of the idling time. What do you have to do? You have to have 24 operations for one, and many of your trucks you have a bell curve of dispatches between 5 a.m. and 11 a.m. With the peak maybe at 9, and you start collecting all your trucks. A big batch of them comes in at 5, and a big batch of them comes in at midnight. But it's possible to solve. Now, where we're going from this point on is, can we handle road conditions, which are dynamic? Can we handle weather, which is dynamic? Machinery malfunctions, can we handle those? And given a scenario, redeploy our dispatch vehicles in some way, shape, or form in order to minimize idling time, manage cost. Those are some of the things we're particularly excited about in this area right now. So I'll pause a second for questions right now, and if I don't hear any, I'll move into some conclusions.
Sorry, I'm still dense on your assumption on land. Are these farmers that are already, some of them already raising switchgrass, or this is assumption that some of the land are already farming, so I can switch the biofuel?
So if I look out on the landscape today, very few people are growing dedicated biomass crops. And therefore, very few people have converted over from what's very profitable in this region, corn and soybeans, over to a dedicated crop. Therefore, in our models, what we've suggested is that we not only have to rent that land, but we have to pay the opportunity cost of growing corn and beans on the same land. And those costs absolutely are wrapped up into these analyses. So you can say that if biomass is being sold at the right price, this is taking care of that, and you should be able to make money on that biomass. We need a consumer in order to make this thing go up. I'll talk about it. You have a problem?
No, you have any. I know it's sold that.
Okay, so the question is now, can I talk a little bit about the displacement of food and grain crops and using that land for biomass-to-bioenergy, which is related to the previous question, which I apologize for, is in regards to whether or not the land costs are, am I assuming that the biomass is already being grown or not, in which we're not. In regards to displacing food grains from lands, well, this is something that's going to have to be played out competitively. I think in order to look at it, particularly from a sustainability perspective, we're going to have to look at what opportunities emerge for the people who are interested in playing in this market, whether or not they may be able to increase their income, increase their employment ability, or other factors in these areas. So we do know that there is a large well of gravity when it comes to processing corn in the Decatur region right now, and the Decatur price of corn is significantly higher than the Chicago Board of Trade price of corn. The question starts to become, particularly if you get biomass to become a true commodity, whether something similar would occur around biorefineries. In some areas, I guess the farmers that I've spoken to about this, of course, they're the ones that are already growing little patches of miscanthus. They are seeing that there is some potential to have to feel good about what they're doing on the land, as well as maybe make some money off of it too. But you have to answer all those questions in order to make this sustainable over a long time. Nancy, your question. And I'll just move it back closer to you.
So my question is when you're using this amount of tons of biomass that you want to this biorefinery, is that pretty much average for, you think it would be a doable amount? Because I'm not sure I want to live near a biorefinery if there's 100 trucks a day going there.
Okay, good question. So in our particular simulation right now, we are seeing that we are going to increase highway traffic as a result of this. As of now, with what I would consider a relatively small biorefinery, I think another 20 or 30 trucks on the highway is probably not going to be something I'm going to feel. Now, that's my opinion. I haven't sat there and watched or counted the trucks. Now, that being said, we do hear that sentiment often that another large industry should not be in my backyard ever, and we always have to deal with this. I think only if you are getting benefits that are paying to the society in some tangible form can we actually start to see those trades occur. But those are very challenging questions. Now, that's part of the reason why I do want to handle that operations management problem at the day-to-day scale, because I anticipate that there are going to be many people who are going to be concerned about what's happening on these roads, and we need to be considering the routing of our trucks as well. That system's just about ready to start doing that. Question in the back? So the question is are we also considering water availability when siting the biorefineries? The current analyses that I presented today do not. We are dabbling with this just now in collaboration with folks at Argonne National Lab. So we're hoping to be able to produce some analyses like that too. We're very considerate.
It's a big concern about restoring grasslands in the state.
Yes.
There's also an opportunity to grasslands in central drainage areas, along roadways, and conservation reserves for and I was just wondering if anybody from your department is really looking at can we do something to plant native prairie grass harvested after July when breeding takes place. The Department of Transportation mows all our roadways anyway, so and we're planting a lot of them like 55 over-harvested late summer in Vale. It seems like we have land already with good source of vegetative biomass. I was just curious, is anyone looking at these calculations? Because the farmer already has land in CRP land, and if is allowed to mow it later in the season and harvest it, then he's not taking the crop land out of production. I was just curious if anybody was looking at that issue.
Let me try and capture your question, and I'll also go ahead and start moving into some of the slides I wanted to touch upon because you're hitting them perfectly. I'm glad you asked. If you tied me down, so the question is whether or not people are looking at the ecosystem benefits that may also emerge if we were perhaps a little bit more clever about maybe taking advantage of CRP lands or reestablishing grasslands or considering waterway impacts and what have you, particularly from an ecosystem or ecological perspective. It depends on who I'm talking to. I tell people I'm often a systems engineer, but if you really pulled my arm behind my back, I'd want to say I'm an ecosystems engineer most of all. So yes. So the short answer to your question is very much yes. And here's some of the things that I've learned in regards to some of the ecosystem impacts. I'll say first, it depends on whether or not you really want to go all the way to a monoculture or not. And there's benefits and costs to both, just like any other system. The simplest way I think I can describe it is that corn is one monoculture that's already around here. It'd be nice to have something nearby it that would create a new habitat. But it depends on what grass you decide to put there. Some of the miscanthus type grasses are not showing diversity benefits or proving to be good habitats for native or migratory species that move through our region. Switchgrass, which is an example of a prairie grass, even if it were planted in a monoculture, is showing some major differences relative to corn as a monoculture or miscanthus as a monoculture. If you go all the way to a mixed prairie grass, of course, much, much higher still. So there are some ecosystem benefits that probably could be sold to taxpayers in one way, shape, or form. Now, related to that, there is research I want to make you aware of at the Energy Biosciences Energy Fund that is considering the different types of ecosystems created and the yields of different types of mixtures of prairie grass, the miscanthus monocultures, the corn monocultures using stover, as well as switchgrasses. So there are people looking into not just how much you can grow, which is a very agronomic question, but also what might be some of those ecosystem benefits, including things like not just the benefit of new habitats that are created, but also maybe consider concerns of invasiveness or water impacts downstream, although I would like to see more work in that particular area as well. Now, related to this, and the reason I pulled up this particular slide on the lower right, there is a project that's also emerged as an offshoot of this, funded by the Illinois Department of Transportation, where they're looking to see about planting biomass crops. And some of your folks over here at STC are generously giving their time too towards studying some of this work as well. And the idea being, like, if you're going to grow along the median, well, what piece of the median as well? Some of the highlighted red areas would possibly flatten up away from the utilities and what have you, could be grown in biomass. But there's a whole new logistics challenge that emerges because your farms are way smaller now, probably a lot more distributed. But it's still close to the highway, though. Maybe that's not so bad. So there'll be some costs and benefits I expect there as well. How am I doing? 5 to 10 minutes? Okay. So I'd like to take this opportunity to highlight a little bit of the other work too. That's a website I manage. These are some of the views of some of the research projects that we go on. We're going to use very similar techniques for some of the other aspects of sustainability that we like to study. Almost identical techniques that were utilized today we're going to use to study food security in the way of preventing post-harvest loss of grain, food grains, in order to see if we can improve our ability to capture some of those grains and make sure they get to a consumer at one point or another. Some of the suggestions around the world are that post-harvest loss of food grains can be as high as 50% in parts of the developing world. And this all occurs before it gets to the consumer. In the developed world, the problem is much more different. We actually are doing a pretty good job of delivering our foods to the consumer. It's the consumer that's throwing away half of their food. And maybe it's because it's so inexpensive. And that's just not true in the developing world. So we're hoping. It turns out that the similar optimization approach can be quite beneficial in those aspects as well. And the idea now, it's a multi-optimization problem. We want to minimize not just the cost and make it affordable, but also get rid of some of the loss pathways if we can identify them there. We're pretty excited about that. I mentioned IDOT and what we're doing with them as well. The remaining projects are actually very focused on environmental impacts. This is where I get to get my ecology out. But we are looking at ecosystems and best management practices handling agricultural runoff waters. We're studying the reliability of those microbial ecosystems. And we're also looking to scale those up to identify what are incentives that we might be providing to farmers and other folks within our economy to actually start implementing these on a wider basis. That work is particularly targeting hypoxic zones in the Gulf of Mexico that are generally attributed to non-point source pollution generated right here, right near where we are right now. So we'd really like to get that project to grow. The other two projects, we're looking at potential for greenhouse gas balance changes through our agricultural systems. Agricultural systems generate a lot of methane through cattle production. That'll be a function of what those cattle are consuming. But interestingly, manure on farm fields could lead towards, could be the catalyst that leads towards keeping carbon in soils in some suggestions. So we want to know what our potential is there. Can we use the cows themselves to tilt that balance in the favor of keeping some carbon in the ground? And then we're also looking at some of the microbial ecosystems within the soil itself in order to see how can we keep yields high but also poke those microbes in the right way in order to keep the carbon in the soil. I'll also point quickly to the folks behind. I don't work by myself. I already mentioned that the EBI is whole mess of, there's about 20 people working with us just on that EBI program. There's a number of folks working in the lab. If I click again, I'll point right now to Young Chen and Tao in particular. They are current folks that are really right behind all the things that I presented today. They'll be looking for jobs soon. If you're looking for good people, I highly, highly, highly recommend both of them. And just in case anybody's interested in talking in the future, there's a little bit of contact information on me. So if there's any other questions, Nancy, it's up to you. But I'll be here. Thank you.
We could take a couple questions from the audience and then we'll finish up with some other people.
So the question is whether and how good of a job are we doing in utilizing the full capacity of the trucks? It's a really important question, actually. If you transport bales of biomass, you'll fill up the volume of your truck much sooner than you fill up the mass constraint of your truck. So if you're working with bales, you're not. You're really, really not. Now, how dense do you want to get it to? You want to get it to about 800 kilograms per liter. It's pretty high. Yeah, it's pretty high. It's approaching the density of coal is what you want to get to. That's quite high. So one of the things that spawned up right away, because it also impacts that truck idling time I alluded to before, is that a whole research wing really spent time looking at how much energy was involved, how much cost involved in chopping and grinding the materials down, how does that impact, and we did have a whole study that went out. It's going into review right now. I should have mentioned it earlier, actually, where we start to identify what is the right range to chop your material down to that would minimize your cost. There's an interesting trade-off there, of course. You spend more money and energy as you chop material smaller, but it stores better and it transports better. So there is a minimum we can find right there. It's pretty nice. And we take it a step further with compression. We have a pretty good idea as to how much chopping and grinding cost, but compression, particularly at scale, not too many people are doing that. So we can actually show how much you could make at different levels of compression and how much you can therefore spend on that compression technology. So, yes. So the question is does moisture content impact your ability to compress? And the answer is yes. It also impacts your ability to transport. Because of course, transporting your moisture is a problem. Let me make a further comment on that, though, too, because at the biorefinery, particularly since most of our analyses are referring to bioethanol, while you would prefer to receive dry biomass because it's cheaper in the supply chain, you need water again to convert it. It's generally a fermentation process. That trade-off I would like to study a bit more. They kicked us out on that ensilage idea right from the beginning, mainly because of the nutrients that the biomass would require to grow in the upcoming seasons. Now, although that does have some negative connotations in many instances, there's a trade-off. It's an opportunity. We should look at it objectively from a systems perspective, in my opinion, to see, should we replace some of that, paying cost and energy to replace it, and maybe are we still profitable from all perspectives, net energy, cost. Because you will get a lot more biomass, number one, a lot more, factor of 2 potentially, more, as it degrades standing in the field relative to waiting for it to dry down. And maybe if you are well distributed in the locations of your storage, preprocessing, and conversion, maybe there is a potential to make that water useful now when you transport it. Maybe even the nutrients themselves are useful when they get to the biorefinery. Now, you'll have to think about the impact on the yield of the material in the field. Recently, there have been some studies that have shown that some of the biomass crops are responding positively to nutrient additions. It would depend on how much rain you get on any given season, though, too. So it's not a linear function by any means. And it would be stochastic because of weather, for sure.
We do have one question.
So I'll repeat. So, okay. So I'm not studying that that level of efficiency personally, but my current understanding of the energy costs, we have studied them quite extensively. Those costs do mirror very closely the costs that you're currently seeing in the breakdown. That is, the energy for transport, the energy for chopping, the energy for harvest, currently the major cost there is not just the capital but the operations, and the operations is fuel. So if you were to bring nutrient, it turns out that growing grass is relatively low hog when it comes to requiring nutrient, so maybe not that much is my anticipation. And you would see parallel in cost and for the most part. Okay. So where can we look for information on subsidies for renewable energies, and where is the trade-off between wind and solar versus biomass? So wind and solar can be implemented in areas where those natural resources are widely available, which is not everywhere, for the most part, unless our photovoltaic and wind turbine technology greatly increases. So I guess my advice for folks interested in those things are generally to target those areas for regions where they are suited. Now that being said, biomass is the most abundant molecule on Earth, and it is abundant everywhere. And it can be actively grown. So if we can grow it in temperate regions at the scales that potentially are profitable, I would suggest that we could probably do more in tropical regions, although there's less land in tropical regions. So if we are willing to look under, don't forget, biomass is generally what we consider waste. So if we can think about better utilizing our waste, then maybe biomass becomes a little bit more attractive. So the question is whether or not we've looked at corn stover in our analysis currently. I'll say two things about that. Our current funder, our primary funder, Energy Biosciences Institute, is not very keen on corn stover, so we haven't spent too much time. Now that being said, like I keep repeating, I want to look under the hood and under the carpet and under the rug for all of these sources of biomass. I think corn stover is viable out there because, of course, we're growing it already, and maybe now you're multi-using some of this. But there's some sustainability impacts. We don't want to put ourselves in a situation where any sort of erosion, whether it's wind or rain or water erosion, might occur. Now, that being said, how much corn stover can you grab? We usually look at a 1-to-1 ratio between the amount of grain you can harvest off land and the amount of stover available on that piece of land. And you wouldn't grab all of it, you grab some fraction of that stover. So you could probably get a little less biomass than you would get switchgrass from the same piece of land, is the answer to the question, because of that. Now, would that be profitable? Possibly, especially if you're also making corn grain money. Yeah. Yeah. Yes. So the question was, if you're removing 30 to 40% of biomass from lands, what would be the impact? I think there's a lot of potential for moving corn stover. The farmers who I have talked to lead me to believe that there's lots and lots of stover piling up on agricultural land right now. And some of them are getting to the point they're concerned that the stover is inhibiting the crop of next year on renewables, particularly some of these no-till situations, which is a great thing. We don't want to get rid of that. So some would say that removing some of that biomass would actually be beneficial and not sacrifice any soil quality. I would say that we need to test, but the probability is relatively high. So the question is, if we're to get to the billion-ton study, 36 billion gallons of fuel, what is the remaining fraction that would probably be biomass versus other versus corn? Yeah, so we're probably between 10 and 12 tons or billion tons of corn ethanol, sorry, billion gallons of corn ethanol today. And the suggestion that I'm hearing is that we're probably about maxed out without really getting into the food versus fuel concerns any further. Of course, evidently there's enough corn to do both if we're here. That's the suggestion. They are targeting to maximum, to not allow it to go beyond there, but I think that's a political decision as opposed to what can the economy handle. Now, so what is the remaining fraction? I don't think 10% of the remaining fraction is these other advanced biofuels. I think 90% of the remaining fraction would probably be cellulosic. The question is how much of that really going to become fuel if they're targeting 2022, the year 2022, to have that stuff delivered, and we have less than 2 commercial scale biorefineries today. How much can we really capture? So these are nice goals. These are excellent goals, and it's created a lot of opportunities for us on the research side for sure. Some of the industry is going to have to get involved. Yes. 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 Thanks for asking. The question is whether I could talk a little bit about the work in biofilters that we're doing. So these are denitrifying nitrate biofilters. They're wood chip packed biofilters that we would put at the end of tile drains. Tile drains are widely used in this part of the Midwest to allow drainage to occur, freeing up agricultural land. These tiles also become highways of nitrate movement that escapes agricultural fields and ends up in our surface waters and subsequently in the Gulf of Mexico, creating rather large hypoxic zones. Similar hypoxic zones exist in many different parts of the world. Many are also associated with agricultural lands. Particularly challenging problem is a non-point source pollution with the point effect. And the two regions are geographically dispersed. That is, the source of the non-point source pollution is over 1,000 miles away. It's hard to get these two groups to come to a meeting. These biofilters, we're pretty excited about them. They can potentially be installed at the edge of fields, attached to tiles, and maybe not even sacrifice any agricultural lands. We've buried some beneath the ground and planted corn on top without any observable effects. Now, my work has been studying the microbial ecosystems in particular. How are they collaborating with one another in order to, and how can we focus their activities in order to encourage denitrification to occur? We study the reliability in particular because as rain events come and go, and as ecosystem drivers come and go, we do see that the performance does not necessarily stay at a high removal rate at all times, and not all of the upsets can be explained. So there's an opportunity to perhaps create a new design factor in the way of reliability, and I am referring to an approach to fundamental engineering reliability, and use that as a design factor to help us size and control these bioreactors by better understanding those. So yes, rain events are a huge impact on reliability, but then the actual structure of the microbial communities and the way they hand off nutrients to one another in the denitrification pathway actually does have some impact, and we could probably do a better job of that. So the question becomes whether I'm aware of the work at ISTC and particularly the potential concerns of methylation of mercury with these bioreactors. I'm really intrigued by that particular issue as well. I've spoken to Dr. Cook. Richard Cook is my primary colleague on this work, along with some folks from civil engineering and environmental sciences. Methylation of mercury, I've proposed a number of times that we can look at our approach for reliability and kind of turn it backwards, where the failure of the system would be the creation of methylmercury. Now, so far, we haven't actually spent too much time working in that particular area, but I think I do see some potential that we can have some positive impacts. I also am aware, I guess I'll say, that some redesigns to the biofilters avoiding long-standing water at the bottom of these biofilters probably has a lot of impact as well. And I guess at that point I'll also mention that removal of phosphorus or phosphate can also be brought into these reactors with some pretreatment in a smaller physical chemical system.